Okay, so the first thing we're going to do is look at the Western Online class page, just quickly review the dates for the test and how the structure looks like. So I'm going to start from a clean slate this time, so none of the old documents are here. So here's the syllabus, and let's just quickly review the dates. The dates are all here now. February 24th would be the first test, March 31st would be the second test, and April 28th would be the third test. And then we will have a comprehensive final on the 10th. May 10th happens to be the Tuesday. And so the time for that is double the amount of time than the usual time. And in fact, we can go a little bit over that if we need to. So that's the schedule for the test. We may do the tests in person. I don't know how things will be, but if we do them, they will be in 205. But we'll see. I'm not have not made up my mind yet. We'll see how you guys feel about it. So we can do, in the classroom, if that gives a much better feeling. Okay, then the other two sections in the course are the daily lecture notes. So you have the lecture notes from 2 days ago on Tuesday, and it's just a PDF. So you can click on it and take a look, and it just looks that. So it looks slightly different from the one I use, right? It has this grid. The grid doesn't show up here, but that's okay. I don't think that's a huge problem. And then the additional reading, I just populated it. There are quite a few external resources. If I'm going outside of the textbook, then I will provide those materials to you. For example, we are actually going to look at first three of these, first four of these today. The last one we will take a look at later. So Griffiths, which is the undergraduate E&M text, has this front flap with the important formulae, the Maxwell's equation in general, in vacuum and in matter, the definitions of the fields, the potential definitions, Lorentz force law, energy, momentum, power, all of those quantities, fundamental constants, and then the spherical and cylindrical coordinates, coordinate transformation. So how do you express Cartesian coordinates in terms of the spherical or cylindrical coordinates, or the transposed, or let's say the inverse relations, which is getting r theta phi or s phi and z in terms of x, y, z. So those are there, and the unit vectors. The unit vectors are crucial, especially important in E&M and also in classical mechanics, because it turns out for solving problems in classical mechanics also, if the symmetry of the problem is spherical, it is much, the equations of motion in the spherical coordinates have a much simpler form. And for that, you need to know the unit vectors of one coordinate system written in terms of the coordinates of the other system, right? And so that's what these things are. And their derivatives, special derivatives are useful in E&M, and time derivatives are important in classical mechanics. So those formulae are there. You don't have to remember them, but it is a good idea to try to develop deeper understanding for them, so it's easier to remember. Vector identities, especially, at least the front flap, you might want to remember all of them. The back flap in Griffiths has these vector derivatives and vector identities. I'm not expecting you to remember those, but we are going to learn techniques to be able to quickly derive those, right? So that's the idea. The thing with being, knowing theory, physics enough is you don't have to remember things. Don't go by the memory. You can rely on your memory, but you should have techniques that anytime you need something, even if you're stranded on a island alone, you should be able to derive all of these things by yourself. That's the idea. So if you don't have any resources, you have this deeper understanding of how things work, you should be able to derive them. That's the idea. And that's the kind of skill level and familiarity with these concepts is what you want to be developing. We will take a look at Dirac delta today. So the discussion of Dirac delta from Griffiths is kind of nice, so that's why you have it here. It starts from that page. This is from scanned pages, so it looks kind of like that. So you get, so it's a copied page and then scanned, so it looks a little weird, but you get the idea. It's there for you to get more help with. Dirac delta function is a extremely efficient mathematical tool for handling a whole lot of interesting situations in E&M as well as in quantum mechanics. And you can even assume a Dirac delta potential and try to solve how a electron passing through that would behave. So it's an interesting problem to look at. And then Appendix A is something we will go over in a little bit. But again, very quickly, the reason why these things are provided is mostly you are responsible for reading them. I will not be going through them in detail. Now, appendices, you may have ignored them in the past, but the gem in the book is actually in the appendices for most of the time, and which is especially true here for Griffiths. He does go into the details of some of the derivations. It's important to know that as a theorist, of somebody who is learning theory of physics. You want to kind of get to that. And the idea here is simple. You want to have a very general coordinate system. In the Cartesian coordinate system, each coordinate has a length dimension, physically speaking. But if you look at, for example, spherical coordinates, two of them are angles. Only one has the distance dimension. That means these two have some, you have to treat them specially, in a special manner. And so that's where, if you look at, for example, a line element infinitesimal displacement vector, right, from some point UVW in this new coordinate system, be it cylindrical, be it spherical, it could be elliptical, it could be prospheroidal, any kind of coordinate system that you come across, you can deal with all of those at once using this formalism. And so if you're going from UVW to U plus du, I'm at this point here in the, look at the mouse pointer. Then what happens, that displacement vector, you want to be able, that's your almost the first step. You want to be able to write that displacement vector down. And in Cartesian, it's trivial. It's dx x hat plus dy y hat plus dz z hat. But when you change into these curvilinear coordinates where angles may crop up as one of your coordinates, there you can't have just theta times d theta, right? Or rather d theta times theta hat, or d phi times phi hat. It just doesn't have the right kind of dimensions. Every term, even though this is a sum of three vector terms, every term has to have the dimensions of length. If it doesn't, then it does not make sense to be a displacement, right? Does that make, is everybody with me? And so you want to turn it into the displacement or length dimension. And the way you do that is d theta will have to multiply it by r in the case of 3D spherical coordinates. D phi would have to be multiplied by the corresponding moment vector, which is not r, but it's a projection of r into the xy plane, which is r sine theta. And so you would have r sine theta d phi. And that is how these things work. And once you have a good handle on that, then you can start to think about, start to generalize and extract, use the general expression to extract the specific relations for any given coordinate system. So here, this last paragraph, or rather the first paragraph on the next page, on page 548, you can see in Cartesian coordinates, F, G, and H are 1. In spherical, F is 1, but G is R, and H is R sine theta, just like I explained to you. And then the cylindrical coordinates, F and H are 1, and then G is S. So that's how all of that works. And here he is calling, normally we would use rho for the cylindrical radial coordinate. Griffiths is using S, so that's only sort of a slight notational difference. But other than that, the idea is the same. And then once you have that displacement vector down, the rest of it is just straightforward. Then you can concoct things like the total derivatives, the gradient, and you can see in the gradient, you suddenly now have 1 over F, 1 over G, 1 over H, these terms appearing. And that's why you have the 1 over R sine theta, D over D phi, those kinds of terms appear because of this general structure. Right? So you could take a look at that. Rest of it is something that you will be responsible for reading through. I would not give you the detailed, the rest of the calculation is straightforward. You can go through that. Idea is to just understand how to write the displacement vector once you get that. And in classical mechanics, we will also be doing the same later on in the summer. So that's the biggest task of the day for you. After we are done here, you can go through that, and then hypergeometric functions, we will take a look at them later. These are again special functions, essentially solutions of the hypergeometric differential equation that some of you saw in your math physics class last semester. Those of you who haven't seen it, you will get to see it briefly this time. So the materials are there. Your first homework will appear on Western Online sometime later today, and some of the work that we will do today will be useful for that. Okay, so I'm going to now start sharing the notepad. Okay, and here's sort of the rough plan for today, and we're mostly going to do mathematical preliminaries. And again, like I said, some of those things I will go through pretty quickly. If you need resources for that, let me know and I will provide those to you. But we are going to use new methods. The math physics, those who took math physics with me are familiar with some of the techniques that we're going to be going through. But those who have not, you can ask your friends for resources, or you can ask me. Either way is fine. I will be happy to provide them. So we just looked at what you need to know about curvilinear coordinates, and I'm just going to add a note here. Read Appendix A from Griffiths. And you don't need to look for Griffiths. I already gave you that. The idea, again, I'll emphasize the word read, does not mean you just read like a novel. You have to go through the mathematics. Developing familiarity with mathematics, writing it down correctly is very, very important for this class. And so develop some comfort level with that material. That's going to be crucial for you. Okay, so I'm just going to continue with the discussion of microscopic and macroscopic domains. It reappears a number of times in this class, because you do have to make that distinction all the time, because the charge density or the current density distributions, they change enormously as you change distance scales. If you go to the atomic distance scales, then you will see that you will encounter enormous amount of charges and enormous amount of electric and magnetic fields when you are very, very close to the sources, the charges or the currents, or you're basically going very close to the atoms inside any material. And so the way you would deal with E&M at that stage is very different from dealing with electricity and magnetism at the normal distance scales, which is bulk matter. if I give you a block of iron, you would treat it as a macroscopic block of iron, not worry about how the charge distribution is inside. You're going to follow some sort of an averaging procedure to be able to deal with macroscopic material. So understanding those differences is crucial. And once we get those, then we are going to be able to make sense of this, right? So we talked about the idea of surface charge density, or surface current density. Both of these are idealizations within the context of classical electrodynamics. Now, if you go to quantum electrodynamics, then there would not be idealization, because then you are allowed to go into the small distance scales, you can trace out how things are. And in that microscopic distance scales, you would have smooth variations. So here, for example, if I were to plot a situation where you have the surface charge density, I'm going to call it, I'm going to talk about it as a volume charge density, right, as a function of, let's say, the radial coordinate. So at some specific, so imagine a sphere that is a hollow sphere, so there is no charge inside, only charge on the surface, right? So in that case, and the sphere radius, let's say, is capital R, in that situation, you don't have any charge. So I'm going to now use a different color for charge density. Let's say you have no charge inside. Suddenly you have a large amount of charge and certain value for rho, and then outside there is no charge. So this is, in some sense, a very discontinuous, right? Density distribution. It's the density of the charge density, of course. You can have similar things for the current also, right? So things are rapid and happening very quickly, right? That the width, even though for visually making sense of this, I took the width of this to be very small. I'm just going to actually call it, let's say, delta R, right? The width of this function is extremely small, but it's, in reality, or rather, in this ideal domain that we are studying, delta R tends to 0. So that means you have a very, very sharp spike. Such spikes don't exist in real world, right? If you go to the appropriate distance scale, so over on the microscopic scale, so so these discontinuities exist only in the macroscopic domain. That means you are working at distance scales where these changes happen so rapidly that if you plot it, just like I did here, you can see rapid changes, right? You will see maybe a step function arrive, or this one is analogous to what we call delta function in physics. So these things arise only in the macroscopic domain. Microscopically,
Dr. Kapale?
yes.
Yeah, the page is going to be out of the screen, I guess.
Is
So
it okay? So let me move that. Thank you. How about now?
it's good. Thank you.
Okay. So microscopically, we do not have sudden changes or discontinuities. And things change smoothly. Okay, so that's the idea. Because you are at a smaller distance scale, you can figure things out easily, right? So imagine you have a bicycle that is very, very small and you have a very rough road, right? And rough road with, let's say, some wavy kind of pattern. If you have a normal car going over that road, you would feel that, there would be bumps and it would be a rough ride. But if you have a tiny bicycle or a tiny vehicle, that is has a much smaller distance scale, compared to the variations, then it would be a smooth ride, right? You would go smoothly over the variations and so on. So it's, just I'm just trying to help by giving you a simple mechanical model that you can relate with to understand that. So the true microscopic theory, so these things are useful, or rather the theory that you need to understand things at the microscopic level is quantum electrodynamics. And here, it's not just the charges or uh, the currents that would be smoothly varying. It applies to all of the electromagnetic field parameters, right? So the large distance domain of quantum electrodynamics is classical electrodynamics. So you go into those changes. So let's take a look at now, how do we mathematically express some of these macroscopic electrodynamic quantities, right? So because in this class, we are going to deal with macroscopic domains. That means, okay, so let me first tell you the distance scales here. That's crucial. Distance scales are of the order of the size of the atom, right? So it's going to be 10 to the negative 9 meter, about a nanometer distance sensors, and that distance scale, things are just moving very, very smoothly. For the macroscopic domain, because there are discontinuous jumps happening, we need to be able to express those in a mathematical form, and that's where this graph that I described to you comes in. We describe the volume charge density of a let's just write it as a function of the magnitude of the radial coordinate. It becomes some surface charge density sigma times delta of r minus r. I'm going to just put it that way. And so that's because it's the delta function is vanishing at all points except when the argument is equal to 0. When little r is equal to capital R, delta function doesn't vanish. Outside of that, it vanishes, right? So that's just the definition of the Dirac delta function. We will, of course, take a look at that in more detail, and I'll write it down later. But that's now a true macroscopic surface charge density. So like I said, you need to make friends with the delta function. We encounter that quite a bit. It becomes useful for being able to derive this. The electric field in that direction, let's just also use r radial coordinate, it actually now becomes a theta function. So inside you have no electric field, but now because you have the surface charge, the moment you pass the boundary from inside to outside, you suddenly have electric field outside. And so this is now the jump, rather I should say sudden jump in E field across the boundary. right? And so how does that happen? So it depends on sigma, of course. Later on, we will learn how to calculate these things. For now, I'm just going to write it down for you. Okay, so there is this something called a theta function. So this is a delta function. It's actually called Dirac delta function. And that's a step function. And let's do a plot of the step function. It's actually fairly easy. And I'm going to do a plot again, like in the case of the earlier situation. So for the, let's change the color, for R less than capital R, you are over here, so it's 0. Let's make the scale to be from 0 to 0 onwards, right? So it just increases there. Doesn't look like a 0. And in the domain of, the domain outside the sphere, you're going to have a sudden jump, right? These things are macroscopic, right? So let me just write down here. Microscopically, if you wanted to see that small variation, if you were to kind of zoom in the domain of R equal to R, what you would rather see is, and let me use again a different color for that. Right? Let's do this. So over there, you would see smooth variations over some distance scales. Again, now the distance scales used for the microscopic and macroscopic are very different, right? So don't compare, you need to be careful when you're comparing them, but you are going to have a smooth variation like this. Only when you go into this macroscopic domain, there the smoothness goes away and you have sudden jumps. Okay, so that's good enough, and that's at a very different distance scale, right? So you need to remember that. Let's write that here, actually 10 to the minus 9 meter distance scale, and this is several centimeter, let's say, distance scale. Okay, everybody with me so far? Does that make sense? Okay, so this is crucial in ENM because you always have to do that. Now there is of course a rigorous procedure how you would go from, let's say somebody gave you a microscopic charge distribution. You have atoms in a solid, and you know how those are arranged and so on. So that means the charge density distribution, which is lots of delta functions situated there. How do you go from that microscopic description to macroscopic description? There is a set procedure for doing that. And we will be doing that. The book talks about it in greater details, and we will be using that. So when there is a time to solve a problem, then we will take a look at how that procedure works, right? So there is a certain averaging procedure. So everything is mathematically as rigorous as it can be in physics, right? If you tell that, so the mathematical rigor in a physics class, if you communicate that with a mathematician, they're not going to like it, right? They are more purist than theory physicists, but you get the idea. Okay, any thoughts, any questions at this time? Okay, no questions. Then we get started on the mathematical stuff, and make sure you have access to the book. Purchase it whichever way. You need to have access to at least one EM book, and this one is as good as any. So make sure you get that, because I'll be skipping quite a few things, right? So basics especially, I'm not going to go into the details. So the next set of topics, so what we should do maybe now is just quickly go over the mathematical stuff from the book directly, so I don't have to write it down. That will speed things up for us, and we can take a look at this. And let's let me focus your attention to the quote here. It says the enormous usefulness of mathematics in natural sciences is something bordering on the mysterious, right? So it's like there is this hidden universe, hidden mathematical universe underneath everything that happens in the natural world. And that's the language of the natural world. And sometimes you encounter mathematical situations that are extremely difficult to describe in words, especially in quantum mechanics, for example, which is something that I fiddle with every day, if you will. Okay, so vectors, you know them, right, quite well. We are going away from our standard x hat, y hat, z hat notation. We're going to go to even e to e3, and then you know the properties of those unit vectors. The caret on the top means it's a unit vector. The dot product of the vectors with itself is 1. They are unit vectors. They are orthogonal, meaning if you take dot product of any two from the triplet, you will get 0. That's just even e2 cosine theta. Cosine 0 is 0, right? No, cosine 90 is 0. Cosine 0 is 1. And so that's how you get the dot product to be 0. And the structure is such that they are orthogonal. That means if you take, and an important thing again is to remember right-handed coordinate system. And that becomes a little tricky to show you visually here, because if I use my right hand to show you the right-handed coordinate system, at least for me in the video, it looks like it's a left-handed coordinate system. I don't know how it looks for you, right? So I can't be sure what you see. And so we are going to not try to develop visual models for that, right? So we just stick, just to avoid confusion. So that's the right-handed coordinate system. So any vector, you can write it down into its basic components. In the math physics class, we went quite deeper into a more abstract linear algebra, where you don't necessarily have just 3 components, right? You may have many components, right? And so that's the idea. Here is how you would write down that vector component. If you change your coordinate system from ek to ek prime, a very different coordinate system, either you start with certain coordinate system and rotate it, which is very often very useful, or you have a completely different coordinate system, like going from Cartesian to spherical or cylindrical. And in that case, you will have a new decomposition. The vector does not change. The vector that you have has a specific direction in space, a specific origin, and specific endpoint. That does not change. What changes is when you change your coordinate system, the components change, right? And so that's not a new vector. It's the same vector physically, but it's the components are the ones that change. So you need to be kind of mindful of that. Here is a picture A and B that talks about the cylindrical and spherical. And just as examples, Cartesian coordinates written down, a definition of the divergence, which is the gradient operator applied to V, because gradient is a vector operator, right? This is how it's defined. You know that quite well. X component of the gradient is a partial derivative along the X direction. Y component is the partial derivative along the Y direction. And the Z component is the partial derivative along the Z direction. And that means if you have a certain field, you would first figure out what your coordinate system is. You figure out how is this field changing in the X direction, find the derivative, and that's the X component of the gradient, right? And so gradient itself, once you apply to a certain field, and what do we mean by field? Field is basically a quantity that has a specific value at every spatial point in space, right? So it doesn't matter what coordinate system you use to describe the space that you are interested in, but field has a specific value at each point, right? Inside your room, for example, where you are right now, you have a temperature field, right? Closer to the vents, it may be hotter. As you go away, it may have different values. So temperature is a very good example of a field that we experience around us. If you go outside, it's crazy cold. And so you have a very different values of the temperature outside compared to inside. right now. So that's what the fields that we encounter in ENM, they can be both scalar and vector, right? So the meaning, I'm not saying one field will have both scalar and vector components. It's, different type of vectors, different type of fields. Some fields are scalar fields, some other fields are vector fields. Meaning a vector field is a lot more complicated. At each point, you have a vector that is necessary to specify the value of that field. It's not just one value. It has a coordinate and a direction as well. Now, of course, if you want to be more specific about that, in the math physics class, we studied the difference between the interpretation of a vector as just magnitude and direction versus specific transformation properties that it has to satisfy, right? So keep that at the back of your mind. It's useful in ENM as well. In fact, one of the prime examples comes from ENM. Then the cylindrical coordinates, again, the descriptions, the transformation from Cartesian to cylindrical or back are given there. Cylindrical is much simpler because there are only two quantities that change. Z is exactly the same. So it's sort of almost like a plane polar coordinate, and Z is exactly how it would be in the Cartesian coordinate. So based on that, you can do this. Here is the gradient operator. The appendix in Griffiths that I showed you, you can use that to derive this, right? So here, it's just listed as what the gradient operator would look like in the cylindrical coordinate. It's not listed as a, it's not derived here, but you want to understand how to derive it, look at the appendix that I shared. Dimensionally, it's very easy to see. Rho coordinate has the length dimension. So this term, component of the gradient in the radial direction is going to be essentially just a partial derivative d, with respect to rho. And you can see the dimension of this quantity is 1 over distance, right? And so if you look at, for example, the phi derivative, so if you wanted to find out the component of the gradient in the phi direction, you can't just write down derivative with respect to phi. It just does not have the 1 over length dimension. That means you have to divide by a length-like quantity, which naturally is rho here, right? So you can at least, develop some sort of a trick to quickly check if the expressions make sense or not, right? And then Z, of course, there is nothing new, right? Z is a distance coordinate. So the Z component of the gradient would be the partial derivative with respect to Z. Okay, so this is only one term that is special here, and you develop, or you keep in mind these rules of thumb, so that you can make sure when you're writing things down, aid your memory by having these concepts at the back of your mind. Again, no derivations here, just the list. You will not be required to remember them, at least for this class, because you will have, it's open notes and open book test, mostly open book actually. And so it's a good idea to at least know how things are and quickly check and not make mistakes while copying things. But other than that, it's easy. But, like I said, my metric that you should follow is, if you're stranded on the island, you should be able to derive this on your own, right? So that's the idea. So develop that kind of skill level and familiarity. Spherical just gets a little bit more complicated. You have two terms that are odd, right? This one here, partial derivative with respect to theta, needs 1 over r there. Partial derivative with respect to phi, you need 1 over r sine theta there. Again, why sine theta? Because it's the r sine theta component, that's the moment arm. If you change the phi, the amount of change that happens in the 3D space, right? Let's say you have a vector that's pointed in the xy plane, and you change the vector is here, right? The projection is in the xy plane. If you change the angle by phi, phi plus d phi, you change that angle, the amount of change that happens, the change in the vector, the dr, is governed by not r in that case, it is governed by r sine theta, right? Because r sine theta d phi is going to be the length change in that vector. That's why the sine theta, right? So sine theta is dimensionally not necessary, but it's physically necessary, because that's the moment arm when you change phi, right? So you need to understand how these coordinates are related with each other to be able to remember this. So r sine theta d phi, you should never forget, right? That's always how it's going to be. Okay, and then you get the divergence, the curl, the Laplacian. Laplacian is just the divergence of a curl, and then then you get del squared there, and so on. Okay, very good. Any questions so far? Okay, so make sure you can derive those, right? The book doesn't expect you, but I do. So make sure you go through the appendix in Griffiths and go through that. Einstein summation convention, extremely useful technique. We're going to use that very, very often in this class. It just makes life easier. And Einstein did that when he derived his special theory of relativity and general theory. It is more useful in the general theory of relativity, but useful anytime you have vectors. It's useful. So let's, for example, look at this expression here. Divergence of a D is written down as, right, it's a scalar quantity eventually, but there are now, each one of those are vectors, and so you can write it as del k, or the gradient k, so the kth component of the gradient applied to the kth component of dk. So let's see how that works. Actually, I will stop sharing it here, and we will do a quick write up from a notepad so that you kind of understand some of the important steps there. Okay, there we are. Let us take, for example, a vector D. Right, so we're going to now look at the Einstein summation convention. If you're familiar with this, again, this class is a mixture of brand new students, those who did math physics with me, and those who did not. So I might go slightly deeper into some of the basic things. So those of you who are familiar with it, just bear with me. It won't take very long, right? So you have a vector D, which has, let's say, components dx, dy, dz, and I'm going to use Cartesian just to keep life simple, but idea works in other cases as well. Gradient operator, of course, is del x, del y, del z, and here I mean del x is just 1 over partial derivative of with respect to x. Sorry, it's not 1 over, it's actually partial derivative with respect to x, right? And so on. So that's how I define them, and those are the components. Now, if I want to take the divergence, which is the gradient operator applied to, so you have a gradient is a vector operator, and then you have another vector. So with the gradient operators, you can do a variety of things. You can apply it to a scalar quantity, and it's going to give you a vector in the end. If you apply it to a vector quantity, there are two ways of doing this. One is through a dot product, and the other one is through a cross product, right? And that completes the set of operations that you would have between a gradient and a field, right? And so you have the curl and the divergence, and that's all that you need. Sometimes, of course, you have double curls, double divergence, because you have, based on the nature of these quantities here, right? So let's take a look at divergence of D is going to be essentially a dot product. So it's going to look like, the order is important, del x applied to dx plus del y applied to dy plus del z applied to dz, which you can write that down as, okay, I'm going to now do one more small notational change to illustrate the Einstein summation convention. So I'm just going to call it D1, D2, D3, and this as delta 1, delta 2, delta 3, or rather del 1, del 2, del 3. And so this then becomes, this would then become del 1, D1 plus del 2, D2 plus del 3 T3, which is sum over I del I di, where I goes from 1 to 3. And according to Einstein summation convention, you just write this as del I di. When an index repeats, you don't need to write down the summation. It's understood that there's always summation involved, right? So you have to kind of make sure that you understand that this actually, because I runs over 3 values, it's a sum of 3 quantities. Okay, so that's all there is to it in Einstein summation convention. For the classical electrodynamics part that we will do in this class, we will, you won't need much of these things except when you're doing vector manipulations. When you start studying tensors and the relativistic electromagnetic theory or field propagations and quantum electrodynamics, then you need the Einstein summation convention every so often. It's a daily thing that if you're doing quantum electrodynamic calculations. So that's that. You can apply similar ideas, of course, to the gradient operator, but the curl operator, but it won't appear there just yet. We will look at that later. So Einstein summation convention is going to be useful. Another couple of symbols that are going to be useful are the Kronecker delta. This is not a delta function that we have seen earlier today. It's a different quantity. It's an index quantity, so it's discrete. It has 2 indices, and that means it's actually a tensor, and it's the simplest tensor that you can write, which has only 2 values. When the indices I and j are the same, then you get 1. If I and j are not the same, then you get the value 0. So that's the Kronecker delta. Then we are going to again use another symbol, which is called the Levi-Civita symbol. And we call it symbol here, but it's actually again also a tensor, which is the simplest 3-component tensor that you can write, or tensor of rank 3. This is, let me just make here tensor of rank 2. Vector is a tensor of rank 1. Scalar is a tensor of rank 0. That means, vectors and all of these weird looking quantities which have multiple indices, they are all tensors. So tensors is a more general encompassing quantity. Tensor rank 0 is a scalar, tensor rank 1 is a vector, and then you can go, of course, go beyond that. And epsilon ijk, which is the Levi-Civita symbol, is a tensor of rank 3, but the simplest tensor of rank 3 that you can write. Simplest antisymmetric tensor of rank 3 that you can write, right? So why antisymmetric, which will be clear here in a moment, and then 0. And if you have the ijk pairs, we're going to stick with Cartesian, right, for now. So ijk pairs can take 3 different values. You can have x, y, z, and if they come in that order or any permutation of them, we can actually write down the permutations on a little mnemonic diagram here. Okay, in Gauss, I'm going to write x, y, and z. So if you're following, the permutation follows that circular path, then it's a symmetric side of it, and then you're going to get epsilon ijk to be 1. So x, y, z works. You start with y, then y, z, x works. Or if you start with z, then z, x, y works. All 3 of them are permutations, are even permutations. So these are called even permutations. And they would the Levi-Civita symbol would lead you to a value 1. If ijk are not even permutations, that means they're odd permutations. So what happens is you change the order of these things. That means you're not really following the order in this circle drawing that I made. So you have x, z, y. So you go in the opposite direction. Same thing for y. If you're starting with y, but you go in the opposite direction, then you get y, x, z. And you're starting with z, but again, you go in the opposite direction of the arrows that I showed. So you go in the clockwise direction, then it's z, y, x, and those are odd permutations. For them, the value is -1. And if any of the 2 indices repeat, then you get ijk equal to 0. right? So epsilon 110 or 112 would be 0, for example. You don't, of course, have to use XYZ as symbols, just like we used 1, 2, 3 instead of XYZ here. You could do that as well, and it doesn't change because it's just the index, right? So index can have arbitrary, notation that you want to use. So let's now do some activities, which is trying to. So let me ask you, let's first deal with the delta function, rather the canonical delta, and let's see what you, so take a minute and tell me the value of this. What is delta kk going to be? Has two indices. That means Einstein summation convention is useful, important, and we are dealing with a 3D space, and so everything is for 3D, right? That means 3 indices. So with that information, all of you send me a chat message directly to me, not to the whole class, right? So you can send me a private message. I'm going to open up the chat. So where it says 2, you can change it to a specific person and give me the value of delta kk. Okay, whatever you feel like the value should be. Okay, I'm beginning to get answers. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I only have 10 answers. How many of you are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let me see. Yeah, we have 15 of you, so not everybody has answered. Do something. Yeah, everybody needs to answer. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I still need 3 of you to answer. If you haven't, it doesn't matter whether you're right or wrong. That's not what, you're not being graded for it. I'm just trying to see what you have, where you are, so we can. Shouldn't take that long. Okay, so all right, so let's take statistics here. I have 2 zeros, so I'm going to write here answers. 0, and I got 2 of them, so that's the stat, right? That's just the number. 1, I have many more. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I have 9 ones, and then only 1, 3. 1, 2, 3. Yeah, only 1, 3. So which one should we go? Should we go with the majority? Is the majority right? Right? They have these, game shows on TV, and sometimes you can ask the audience. And most of the time, if the audience goes with a specific answer, for trivia, more people say the same thing, the better it is, right? But this is not trivia. So okay, so majority is saying 1. Do you think that's correct? Can somebody tell me why it should be 1?
Because I is equal to j, then
I is
after
equal to j. That's right. So delta ij is 1, right?
yeah.
Okay, so that's why it should be 1. Everybody agrees, right? Is it correct? No.
Yes.
It's correct. 1. It's not. You forgot.
You said in 3D, right?
Einstein summation convention. If an index repeats, summation is
3.
implied.
It will be 3.
So this is going to be sum over k going from 1 to 3 delta kk, which means it is delta 1 1 plus delta 2 2 plus delta 3 3. And what is that value?
Definitely
3.
3.
That is 3, right? So that's 3. So the answer is this. This answer is correct, not that. So you get the idea. Okay, so let's now take a look at some of these you will be actually deriving in your homework. So your first homework is going to require you to play with this a little bit. Okay, so I'm going to just use one identity here, EI, EJ. Can we write this in terms of the delta function? Again, I'm looking for answers for this one. I want to use the Kronecker delta to write down the dot product of the two component vectors EI and EJ. Do you think you can do that? You can again put your answer privately to me in the chat once you have figured it out. Okay, I haven't. Okay, delta IJ. Sorry. Yeah, I'm expecting an answer from you. Yeah, it's difficult to write that stuff in the, the correct Quigley delta in here, but you just write delta if you want to in the. Okay, so look, I got 3 answers so far, and they're all the same. So it looks like you have figured out what's happening. Okay, I'll wait for the other ones to write. Remember, I will tell you I and J both run over 1, 2, and 3. Okay, so that means there are different values I and J can take, and so this whole dot product can take many values. It's not one single value. Okay, you guys are a lot more slower in this one. Last one you answered very, very quickly. What's happening? Okay. Okay, so let's think about this, right? If I is equal to J, so I'm going to break your chain of thought now, and let's come back to what we're doing here. So if we don't need to check every specific combination of the different values of I. If I is equal to J, then EI dotted with EI, it's a self dot product will be 1. And if I is not equal to J, then EI, EJ, these are perpendicular unit vectors, and so it's going to be 0. And so that's exactly what the definition of the Kronecker delta is. And so this is going to be Kronecker delta, right? So it just helps you simplify things quickly. You don't have to be specific. You don't need to know the indices. Delta IJ will pick up the correct value for you. Okay, so that's how it is. Another place where delta IJ would appear. Okay, so let me take one more example. Is partial derivative with respect to k. So the gradient, right? The kth component of the gradient of Rj. Kth component of the gradient of Rj, the jth component of R. What is that going to be? Okay, so it is like partial derivative with respect to x of, let's say Rx. That is 1. but partial derivative with respect to x of ry, meaning the y component, is going to be 0. That means if both the indices are the same, the value is 1. If both the indices are different, then the value is 0. Again, it's delta jk or delta kj, doesn't matter which order you write it. Order is not important for delta, because delta is a completely symmetric tensor. The Levi-Civita is an anti-symmetric tensor, because the order then is important. Okay, everybody with me so far? I'm just going to list 2 identities here. So these are important for the Levi-Civita. There are several other things that you can try, and I will let you approve those in your homework. But we're going to write down these 2 identities and use them for one concrete example of where the Levi-Civita is useful. So you have ijk and some other indices I, S, T, where the first index I is common, right? So the first two indices, first index is common in both of them. The other 2 are different, and this can be expanded as, again, I'm not proving it, but you need to see where this is coming from, right? So first index is common. That means that index is getting summed over. Einstein's summation convention is implied. And so when you sum over that on the right-hand side, you will not have that index remaining. So what we need to do is, sorry, I'm in the wrong mode here. You want to couple or combine J with S and K with T, or you can do combine J with T and K with S, right? So there are 2 types of combinations possible of these indices, and so as a result, you get 2 terms in the expression that you get. So delta JS, delta KT, where we use the blue coupling, and the other term would be minus delta JT, delta KS. Okay, I just deliberately use color there so that you can see where those things are coming from. Okay, so that's one identity that's important. Remember that. This one you want to remember. It's much better to remember it than look up for it. And then let's take a look at a situation where all of the indices are different. It turns out that is given by a determinant of the pairwise combinations of all of the deltas. So the determinant takes care of the antisymmetric nature, and the deltas allow you to couple the indices. So delta Km, delta I P, and delta LQ. So the first one, sorry, I think they go down like that. So delta K is the first one, and then you do all the MPQs. So this is M, K, P, and delta K, Q. And this one is delta I, the second index. And then the other indices in order, MPQ. And then the third index for the first Levi-Civita, delta L, delta L, delta L, and then this is Q, P, and M. So it's easy to write down. Once you understand how the patterning works, it's easy to write down, and you can write down that. And in fact, actually from here, you can prove this, right? So possible to prove if K is equal to M, right? And so you can turn that and then be able to do it. But let's actually use the power of this. So the antisymmetric nature of the Levi-Civita symbol is similar. So these are antisymmetric. Let me make a note here, antisymmetric tensor of rank 3. But this antisymmetric nature is very similar to the properties of the determinants. The determinants are antisymmetric, as you know. So if you have a C a 3 by 3 matrix, then the determinant of C can be written down as epsilon ijk ci1, cj2, and ck3. So that means you're picking out a specific column here. So if you do column-wise expansion, you have this very large 9-term expansion that you write down, where each term is a product of 3 elements from the determinant. You don't need to do that. You can write down the determinant compactly using the antisymmetric property of the tensor. So if you take the expansion by, let's say, the first column, then when ijk are making this even permutation, then those terms will come with a positive sign, and then there are some terms that come with a negative sign, and that's pulled out correctly by the determinant symbol there. You can do the row-wise expansion also, where you would get epsilon ijk c1 I c2 k c3 c2j and c3k. So that's a row expansion. This is column-wise expansion. And if when we wrote these things down, we're using the Einstein summation convention. If you eliminate Einstein summation convention, add the summation sign, and take all the values of ijk and substitute epsilon ijk, then you will see that it actually gives you the determinant, right? So you want to be able to try to practice that if you want to see that. Let's see. Another thing that you can do with the help of the identity that we developed earlier, LMN, determinant of C is going to be epsilon I jk CLI CMJ ENK. This one is again something that you can prove. I will put that on your homework. So in the remaining about 7 minutes or so that we have, let's apply this powerful tensor to the derivative, the derivation of some important vector identities. And again, these are done in Cartesian coordinates. If you do those in cylindrical or spherical coordinates, you need to be very careful about how you apply these identities, and we will take a look at that later. Right? Let's say, so this probably from your E&M class earlier, A cross B cross C, and of course some of you have seen this in the math physics class. We talked about it. Unfortunately, not everybody was in that class, so I have to cover it here. So it's a back cab rule, if you remember. So A cross B cross C is B vector B multiplied by a scalar A dot C. So that's the back part, and then the cab is C multiplied by a scalar A dotted with B. Right? Okay, so that's how that works. Now, how do we do this? To prove this in Cartesian coordinates is a mess. It takes a lot of it. It will take one full page worth of work. You have to expand each one of the vectors into its components, then use the cross product rule in the component form, apply all of that. It just gets crazy. Here, I'm going to do this very, very quickly for you. It doesn't take very long at all. We will be done in the next 5 minutes to be able to do that. So because the quantity that I'm trying to evaluate is a vector quantity, I might as well just look at one component of it. And if I can find one component, I can find all the other components, right? So that's the idea. And the way you write down the cross product is, okay, so we're going to first take this vector and that vector. Okay, and so the cross product is going to be epsilon. Remember, the cross product you know already there is a determinant form, and the determinants have some connection with the Levi-Civita antisymmetric tensor. And so we're just going to use that connection, the similarities there, to write down the cross product in terms of the Levi-Civita symbol. So this hanging index needs to appear in every term on the right hand side. If it's not, then there you are doing something wrong, right? Because that index is not being summed over. You want that index to remain in the end, right? So that's the first index that the Levi-Civita symbol gets. And then the indices that are going to be summed over, you need two of them, right, for that. And it's the first vector, AJ, times B cross C, the second vector in the cross product, K component. Okay, everybody with me? So what we have used here is A cross B is equal to epsilon I j k, the ith component rather, is epsilon I j k A j B k. Yeah. This is what we have used here. Like this. I'm going to put it in the box. Okay, so make sure you understand what we are doing, and that's all. That's going to be very powerful always to figure out these vector identities. So we're going to use that one more time because we still have this thing to figure out. And so you're going to get epsilon I j k, and let's add aj, epsilon k l m. The index that's hanging needs to be here, the first one in epsilon. Then you have l and m, so it's going to be b l c m. Everybody with me so far? Okay. Now all of these quantities are now scalars, right? Epsilon ijk. Once ijk have specific values provided, everything is scalar. So that means they commute. You can change their order, move them around as you like them. And so that's what we're going to do. So we're going to write down. Another thing is I'm going to make this epsilon ijk do the even permutations, bring the k in front. And so this is going to become epsilon kij, epsilon klm, aj bl cm. And you can see this is the product. Similar one appeared here in the first identity, right? So we're going to use those two deltas to write this thing down. And so it's going to be k index. You don't need to worry about that. That's getting summed over, so it's going to vanish. You are just going to have delta il, delta jm minus delta im, delta jl, and then you have aj bl cm. Okay, everybody with me so far? Now, when you're summing over, let's take a look at this term multiplied with that. Right? If you look at just first of the term, it tells you that term will be non-zero only when I is equal to L. That means you can eliminate one of the symbols and put it equal to L, because other terms are going to be zero anyway, so you don't need to worry about them. So I'm going to, the convention that we are going to follow is we're going to stick with the first index, eliminate the second index. So every time you find L, so that means L in this equation or in this part of the term needs to be replaced by I. I want to keep I, replace the second index, and M, whenever it appears, I need to replace it by J. That's the rule when we are taking a look at the first term. Does that make sense? It's just a mnemonic or a rule of thumb that we develop based on the properties of the delta function. And so the first term leads us to AJ, because M and J are the same. So AJ stays as it is. BI and CJ, that would be the first term. When we are looking at this term, then the rule is let's see, the rule is M is to be replaced by I and L is to be replaced by J. And so when we do that, negative sign A, J, B, J, C, I. Everybody with me so far? Okay, now let's see if it makes sense. You're looking at the ith component. So the ith component, I should be a hanging index in both the terms. So I is a hanging index here, and the other indices have to be summed over. I is a hanging index here, other indices have to be summed over. So let's keep the I term here, BI. What is AJ, CJ? Anybody remembers? AJ, CJ with sum over J is basically A dotted with C, right? Everybody agrees? Okay, so it's just using the Einstein summation convention to generalize the expression. You can use it both ways. And then take CI here, and AJ, BJ is basically A dot B scalar quantity. And so if the ith component of A cross B cross C is this, you can convert that into a vector notation. It's going to be now A crossed with B crossed with C. All of the hanging indices that you had, they would turn into vectors. So instead of I, you just convert B into vector, A dotted with C, and CI would turn into a vector C when you take all of the components together. And here we have proved that identity by using the property of the Levi-Civita symbol very quickly, just 2 or 3 lines. Of course, here I went a little slowly to help you develop the comfort level with the manipulations of these symbols. But that's the idea, and you will be doing quite a few of these manipulations in your homework, first homework. Now the math physics students, this may be a piece of cake for you, but that's okay. A little practice doesn't hurt, and so you could. It's this part from here to here, and from there to there, and from there to here. Those 3 steps are very, very crucial. You need to be very careful there. You need some careful observations of things and such to be able to figure that out. But with practice, you can do that. Okay, so that's it for today.